Runge-Kutta questions, page 82. So any Runge-Kutta questions will be theory questions rather than calculations. Okay, let's go. So blah 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 blah. What's mean to say that the local error is order h to the power of k plus 1? So to say that something, we'll just write down a little note to say for us f is order, say, some function g of x, means that the absolute value of f is less than or equal to a constant times g of x. This does assume that g of x is positive. So this is that the absolute value is less than a constant times it. So this is what we'll do. That's our definition. So we would say that the local error, now what are we going to, we get, now this is the local error, it's just saying epsilon. We could just take epsilon there. There's different notations. The absolute value of the local error is less than some constant. Now the k, there's another k here that's a little bit confusing. So we might use a different symbol other than k. So how about we use, we could actually use c. How about we use a? Yeah. Is less than some constant times h to the power of k plus 1, where a is a constant. That's a positive constant, so maybe we'll write that in. Yeah, okay, that's that. That's what it means to say that its order, its absolute value is less than or equal to a constant times it. So now this is the big question we've seen numerous times now. So we want to say, we're going to build this up in a natural way. So the global error, and let's say we're taking the local errors to be called epsilons with no L's on them, is the sum of n. If you're going from x0 to x0 plus nh, you've got n steps, so you've got n local errors. So let's say epsilon 1 plus epsilon 2 plus dot 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 epsilon n. And we're going to work with absolute values here because we want to show that the global error is order h to the k. We want to show the absolute value of the global error is less than some constant times h to the power k. So let's take absolute values on both sides here. Then we can use something called the triangle inequality, which basically says that if you have a sum of local errors, and local errors can be positive or negative, and you want to take the worst case scenario, you want to make this as big as possible, you make them all positive by doing absolute values. And now what we can do is we can use the fact that the local errors are order h to the power of k plus 1, but we won't use k's here, it's a little bit confusing, we'll use a's. So individually, each of the local errors are less than some constant times h to the power of k plus 1. So epsilon 2, the second local error, is less than some constant times h to the power of k plus 1. And again, the fact that the derivative only depends on x is of, it's for accuracy reasons, it's important. Okay, now what we're going to do is we're going to say, well, let's take the biggest one, I think. Yeah, so let's say, do this over here, we'll just use a. Let a be the maximum of the AIs, and they're all supposed to be positive. You'll see we kind of wrote that above. So this is a times h to the power of k plus 1 plus a times h to the power of k plus 1 plus dot 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 plus a times h to the power of k plus 1. Again, what we've done here is we've taken a worst case scenario by taking the biggest possible value of a we could get. And there are n of these now because there was a1 to an, and now we've replaced them all with a times h to the power of k plus 1, so n times h to the power of k plus 1. But now n actually is related to the step size. So we're going to take let xn minus x0. So the range of values that we're looking at, now we've used different symbols for this, let's go with L. So there's kind of an implication that if you're looking at a global error, you've got a final time, a final x value in mind. And the distance between these is made up of n steps. And so we can write n, which is actually a variable, in terms of L and H. Because, yeah. So divide both sides, I guess, by H. And my H's look like n, sorry. So you get L divided by H. And that means going up above, we have the absolute value of the global error going all the way, which is less than or equal to n times h to the power of k plus 1. I can replace my n there with, and where's my a gone? It's just disappeared, sorry. So this is n times a. Maybe I'll just correct this. N times a. So this should be n times a. So I'm going to replace my n with L divided by h. Then I have a times h k plus 1. And what happens here is h divided h to the power of k plus 1 divided by h gives me h to the power of k. So I have L, a, extra equals not needed, h to the power of k. And if you look at it, you have the absolute value of the global error is less than or equal to some constant times h to the k. That is to say that the global error is order h to the k. Okay, very good. Show that if we use, yeah, we've done that. What is the relationship between the kth order Runge-Kutta and the k plus 1 term Taylor method, and why is Runge-Kutta easier to use? Okay, so basically they kind of do similar things, will give you similar answers, but they have the same error profiles. So we've just shown, so it's saying what is the relationship between them. Well, one of them is they have the same error profile. Both have global error, order h to the k. Now we'll just do this little note just to remind you. So this is just a little note just to, from what you possibly should know. So Euler's method is, it's Runge-Kutta 1 and it's a 2-term Taylor method. Previous plus step size times slope. Both of them have order error, global error order h. And then the other one you'd know, Hein, is in fact a Runge-Kutta 2. It uses 2 slopes, and it's, and well, okay, Hein is Runge-Kutta 2 semicolon and 3-term Taylor, both. Now you see Euler is Runge-Kutta 1 and 2-term Taylor, they're the same thing, but Runge-Kutta 2 and 3-term Taylor are not the same thing, but they both have a global error is order h squared. So they have the same error profile. Now the question is, why would you use this complicated Runge-Kutta thing where you have all these formulas versus actually the Taylor methods are quite simple? And the reason is, for the Taylor methods, you need to calculate derivatives. So Runge-Kutta is easier to use. And I think, like, if you have a derivative as it is here, just in terms of x, so there is another answer. We'll get to that in a second. We'll do that afterwards. So because you don't need to calculate derivatives, higher order derivatives. Calculate. So like a 4-term Taylor method, you'd have to calculate a second derivative and a third derivative. Higher order derivatives. Now I haven't written implicit differentiation here because it says dy dx is equal to just a function of x. We'll just make a little note. So note. So an additional possible answer to the first thing is, if, how does this work? So the other connection is if the derivative, big F of x, is, so we can kind of figure this out. So Euler, which is Runge-Kutta 1, and a two-term Taylor will get lines correct, and Hein will get quadratics correct. So is an order or degree k, and I'll explain this a little bit, polynomial. Let's just be k minus 1, I think. Polynomial, both, and I'll kind of explain this with the other Runge-Kutta order k and k plus 1 term Taylor will approximate with 0 error. So just to give examples, so the black is the answer to this question, but these are kind of alternative things to write down. Example, if the derivative is a constant, Euler, which is, remember, Runge-Kutta 1 and two-term Taylor, gives 0 error. So this is degree, there's no power of x here, it's degree 0. The solution to this is a straight line, and Euler's method will track a straight line with 0 error. If f of x is degree 1, so that'll be like ax plus b, Hein, and three-term Taylor. So this is Runge-Kutta 2, and this is three-term Taylor, gives 0 error. And then another note, if the derivative depends on y also, higher order Taylor methods, and not only do they require differentiation, they require implicit differentiation, which is kind of worse again in terms of work to do on behalf of the user. So like the Runge-Kutta and the Taylor methods, the ones that you match up, so the order k Runge-Kutta and k plus 1 term Taylor, they basically do the same thing. They have the same error profile, and they give 0 error when you have degree k minus 1 polynomials as derivatives. So they kind of do the same thing, but the point is, why would you do the Taylor methods? Because why would you use them when Runge-Kutta is easier to use? That's basically the whole point of this. And then we have question D, which says, if k is equal to 3, what is the effect on the local error? So what was it saying? K equal to 3. Now in that case, the local errors are order h to the power of 4. And so what happens if you quarter the step size? Now it's just really looking for the answer. You just have to do, so the answer, what is the effect? If you quarter the step size, it'll be reduced by, well, what'll happen? It'll be multiplied by a quarter to the power of 4. So reduced by 256. Now where is that 256 coming from, I suppose? So this is the note to figure it out. So you can say that the local error is approximately some constant times h to the power of 4. That's in the question. And so what happens to the local error when you reduce the step size by a factor of 4? You're looking at h divided by 4 all to the 4. And this gives you a times h to the 4 divided by 256. And look at the original error. So we'll call this the new local error if you divide h by 4, it's the old local error divided by 256. Question E then says, if k is equal to 4, what happens to the global error if you half? So k equal to 4, the global error is order h to the k is order h to the 4. And we have a very, very similar problem. So the answer here, if you half the step size, just do half the power of 4, you'll get 1 over 16. That should probably say factor of 256, a factor of 16. It'll divide the global error by 16. Again, just to explain it, the global error here is also order h to the 4. So if you go to a new global error where you have divided the step size, you've halved it, you will get the old local error divided by 16. So here's another Runge-Kutta theory question on page 83. Work solution on page 168, but we'll still go through it. I have to pause for some coughing. Okay, so right. Let's read the questions. Let's slow this one down a little bit. So we got an initial value problem and common third order Runge-Kutta. Actually, as written, this should probably be down there. And the idea is you've got next is equal to previous plus step size, and then this here is a slope. It's a weighted average of slopes. You take 1k1, 4k2s, and 1k3. And what are the k's? Well, k1, now remember, all the big F is dy dx, so the big F is a slope. And so if you're evaluating the big F at different points, you are getting different slopes. So k1 is something like the previous slope, or current slope. And then what this is going to the midpoint between, so this is just explaining rather than answering questions. So you got xi and xi plus 1. Well, xi plus h, and h is the distance. That's that midpoint here. So I'll call it maybe xi plus a half. It's a bit stupid, but that's kind of what it is. So this is the midpoint, and then this is an Euler predictor. So it's previous plus the step size is half h, and then it's taking the previous slope. And then k3 is a slope at, so k1 is associated with this point, k2 is associated with this point, and k3 is associated with this point. And what y coordinate do you use at xi plus 1? Well, it doesn't look like it, but it is kind of an Euler thing. Use 2 k2s and minus 1 k1s. So altogether, that's one slope. So this is what's going on here. Okay. Now, beginning at x0, y0, in terms of the curve y to y of x, what does k1 represent? K1 is a slope. So f of x0, y0 actually is, it's actually the slope of the tangent. We'll just say slope of solution. Now it's at the initial point, so I could say actually is the initial slope of the solution. You could say something like that if you wanted, actually. That's basically it. It's just saying it's the slope of the point. B. What does x0 plus h over 2? Yeah, that's the as the picture there. It's the midpoint of the interval x0, x1. That's what that represents. What does this represent? Well, this is an Euler predictor. Because if you look here, you've got previous plus the step size. Well, if it's the midpoint, it's half a h, half a step, and k1 is the previous slope. So it's an Euler predictor for the y coordinate at x equal to x0 plus h over 2. Therefore, what does this represent? This is a predicted, so this is a predicted y, this is the midpoint. So it's an Euler predicted slope, because it's a k, it's a slope. Euler predicted slope at the midpoint, x0 plus h over 2. What's that? Given that this is an approximation to y of 1, what does k3 represent? Well, k3, let's go up, it's at xi plus h, so it's the next slope, or maybe the slope at x, yeah, it's at the next point. So I think, oh yeah, so this is an approximate, this probably is a little bit of, needs a bit of help here. This probably should be y0 is an approximation to y1. K3 represents an approximation. So remember, so y1 is, maybe we'll just draw a similar picture to we had before. So we're going from x0 here to x1, and we have an approximation for the y value here. That's this. So this is the point x1, y0 minus k1h plus 2k2h. Okay, so that is a point that we are. This is a point that's approximately on the curve. So k3 is an approximation of the slope of the true solution at x1. And finally d, what does this represent? It's a weighted average slope. So you got k1, 4 k2s and a k3, and you're dividing by 6. It's a weighted average slope. And that's that. So really, all you need to understand here is the big F's are slopes and the K's are big F's, so the K's are slopes as well. I mean, that's the basic understanding. Okay, and a final question. Now this is similar to other questions you might have seen earlier. You might want to skip it or whatever, we'll see. Okay, so here, so we got a 4-term Taylor using tangent cubic. Using the first 4 terms of the Taylor series, this is what we get for the tangent cubic. Find the equation. Well, it's probably not exactly correct to find. If you subbed in to find the, it's not really given the equation. I'd say the prediction of the tangent cubic for y of x1, I guess. Okay, so scribe how to find the second. There's probably missing this question as well. Like you'll notice this wasn't actually an exam question. Probably would have given it more. So what should have been here is that you have some initial value problem. Otherwise, it doesn't really make sense as a question. So this should have to be in the question. So how to find the second and third derivatives. So you want to differentiate the I suppose the differential equation, differentiate both sides, and if you do that, you will get that the second derivative is some function which I'm calling big G, and it'll depend on x and y. And if the y actually does appear, implicit differentiation would say that the derivative of y is dy dx. But then you can use the fact that you know dy dx in terms of x and y from the differential equation to in fact write this in the form xy big F of xy. In other words, you can find the second derivative, i.e. in terms of x and y. Do note it is kind of annoying because you have to, well, differentiating left hand side is grand, but you have to do implicit differentiation. Like for example, if you had dy dx, for example, even like write down something relatively straightforward, x squared times e to the sine y, for example, the implicit differentiation gets a little bit nasty there. Like even just to write it down here, and I'm not spending time on this right now, but you'd get x squared times e to the sine y times cos y times dy dx plus e to the sine y times 2x, and then you after that you've put in the dy dx equal to x squared e to the sine y. Anyway, so that's how you find the second derivative, and then differentiate again to get the third derivative. So I mean, how do we write this down? I suppose if you differentiate, so this function g of x and y can actually be written, maybe we'll write it as, say, g prime. It actually just depends on x and y. So for example, here you can put in that equal to x squared sine y, and you get some function of x and y. Now if you differentiate some function of x and y, you get some other, you get x's, you get y's, but you also get dy dx's. We've just seen that above. But as we said, you can replace the dy dx in terms of x and y, because it'll be f of xy, and that is, i.e., in turn, and that this gets really nasty, like differentiating this thing here a second time. Oh man, that's nasty. That's why we don't terms of x and y. That's why Runge-Kutta is preferred to Taylor methods. Okay, this question we've really seen already, so I don't think I'm going to do C, because we can just look ahead. Or yeah, so question B has been answered, I believe, up here essentially. So to say that the, what is it, the local error is order h to the 4, you just write down something like this, and then you have to show that the global error is order h cubed. Well, just run through all of this except with h to the 4s initially and then h cubes. So we've seen this loads of times. I really don't think it's necessary to go down again. And then effects on global errors, we'll answer this one. So the effect on the global error if we halve the step size. So C, B, and C are above. Very similar to above. On part D, what is the effect? Well, it says the global error is order, and we should have just shown that it's order h cubed, and therefore if you halve the step size, and if you cube a half, you get 1/8, so reduced by a factor of 8. Now that is a full answer, that's fine. If you want, you could say, well, the global error is some constant, we'll use k here, h cubed. So if you were to look at a new global error and calling it global error prime, not the derivative, and you reduce, here you halve the step size, so you'd have h over 2 cubed, and that's equal to k h cubed divided by 8. In other words, the original global error divided by 8. So that's where that factor of 8 is coming from. What order Runge-Kutta is a similar error order to 4-term Taylor? So here I think what you want to do, if you don't kind of learn it off, is to kind of work it like this. So Runge-Kutta 1, which is Euler's method, is similar to 2-term Taylor. So they're basically the same. And this, what we have here is Runge-Kutta. So which Runge-Kutta is similar to 4-term? So we just build this up. So Runge-Kutta 2, for example, Hein, is similar to 3-term Taylor method. And then Runge-Kutta 3 is similar to 4-term Taylor. So the answer is Runge-Kutta 3. And we've had similar things to this above. Okay.